Welcome everyone to this week's Data Science Seminar. I'm David Bader and I direct the Institute for Data Science at the New Jersey Institute of Technology. I'm pleased today to have Dr. Jeannette Wing join us to give a talk on data for good, ensuring the responsible use of data to benefit society. Dr. Jeannette Wing is the Avanessians Director of the Data Science Institute and Professor of Computer Science at Columbia University. She came to Columbia in July 2017 from Microsoft, where she served as the Corporate Vice President of Microsoft Research, overseeing a global network of research labs. Dr. Wing is widely recognized for her intellectual leadership in computer science, particularly in trustworthy computing. Her seminal essay titled Computational Thinking was published more than a decade ago and is credited with helping to establish the centrality of computer science to problem solving in fields where previously it had not been embraced. Before joining Microsoft, Dr. Wing held positions at Carnegie Mellon University and the National Science Foundation. At Carnegie Mellon, she was head of the Department of Computer Science and an associate dean for academic affairs of the School of Computer Science. At the National Science Foundation, she was the assistant director of the Computer and Information Science and Engineering Directorate, or SISE, where she oversaw the federal government's funding of academic computer science research. Her areas of research expertise include security and privacy, formal methods, programming languages, and distributed and concurrent systems. Dr. Wing has been recognized with Distinguished Service Awards from the Computing Research Association, or CRA, and the Association for Computing Machinery, or ACM. She's a fellow of the American Academy of Arts and Sciences, a fellow of the American Association for the Advancement of Science, a fellow of the ACM, and a fellow of the IEEE. And finally, Dr. Wing is the principal investigator of the Northeast Big Data Innovation Hub.
Thank you, David. Thank you for that introduction. Well, good afternoon, good evening, and good morning to everyone who is in the audience. Thank you, David, for inviting me to speak to the Institute for Data Science at NJIT. I should have people know that this is not my first visit to NJIT, but this is my first virtual visit to NJIT. So I'm going to talk about data for good, ensuring the responsible use of data to benefit society. My first few remarks will be specific to data science and then the Data Science Institute at Columbia. And what I'm going to spend most of my time talking about are different uses of data science in different research areas. So let me start with some general remarks about data science. And I like to start with the data life cycle to show the breadth of what data science encompasses. So we start, of course, with generating lots of data. And data, big data and data science in some sense is not new. If you think about the turn of the century, where the science was really generating lots and lots of data through large scientific instruments like telescopes in the sky, and neutrino detectors in the South Pole, and Large Hadron Colliders more recently, science has been generating lots and lots of data. What is new, and probably why data science has really taken off recently, is data that we, people, generate. And that others collect of us. And so it's data about people that has caused a lot of interest in the new methods like machine learning and AI that analyze this data. So we generate a lot of data, we collect the data, we process the data. By processing here, I include everything from encryption to compression algorithms, and then also more mundane tasks of processing the data like data wrangling and data cleaning. And that we do that before and during the storage of data. We have to store the data somewhere in some medium. And we store the data usually with in mind of, eventually retrieving it efficiently. And so we use database and data management techniques for that storage. Analysis is probably why data science is so hot today, and that is where I stick in all the tools for machine learning, statistical analysis, AI, and so on. After we analyze the data, we spit out some numbers usually, and we need to visualize those numbers. And so we draw pretty pictures so that the end user can actually interpret the results. I wanted to make mention of the last phase in the life cycle that I call interpretation. And I didn't really come to appreciate this phase until I joined Columbia, and I talked to all my colleagues in the journalism school. And they were always telling me the importance of storytelling in the sense of a journalist. And I have come to really agree and appreciate that stage of the life cycle. It's not enough to draw a pie chart or a bar chart to visualize the data. You actually have to tell a story about what am I supposed to get out of this visualization and what am I supposed to get out of this analysis. And this is a cycle. There are many loops that I'm not drawing here, but you can put them in for yourself. Most importantly, throughout this data life cycle, we have to care about the privacy and ethical concerns. And this is something I think is particularly new to this quantitative reasoning field, along with computer science, statistics, and other quantitative reasoning fields. And the newness is that we have to take data ethics seriously from day one. And this will be a common theme throughout my advocacy of data science and data for good. So what is data science? I like to give a very succinct definition of data science. It's a little abstract, but it's abstract for a good reason. I like to define data science as the study of extracting value from data. And there are two important words in this definition. The first is value. Value is subject to the end user. So for instance, to a scientist, the value is actually discovering new knowledge. To a business person, the value is bottom line. How does having this value accrue to my bottom line? And obviously the big tech companies that are really advertising companies, every time someone clicks on a link or clicks on an ad, they're accruing value. And then the second important word in this definition is extracting, and that really refers back to my data life cycle, where it takes a lot of work to get this value out of the data. So I have a three-part mission statement in the Data Science Institute at Columbia University, and I want to share it with you. First is to advance the state of the art in data science, and this really speaks to pushing the frontiers of research in data science. And of course, what's challenging here is that data science itself as an academic discipline is still being formed and formulated. And there are lots of debates at various universities, on campuses, and so on as to what is data science. Is it really a new field? What is it going to look like in 10 or 15 years? At Columbia University, the foundations of data science rests on three pillars of strength: computer science, statistics, and operations research. And at Columbia is especially well known for its strength in OR. And we have an OR department in the engineering school, and we have an OR division in the business school. So these three pillars of strength define the foundations of data science at Columbia. Now, the breadth of Columbia University is represented by this part of my mission statement, which is to transform all fields, professions, and sectors through the application of data science. Everyone has data, and thus I believe everyone can benefit from the methods and tools of data science. And sure enough, when I have gone around throughout the entire campus at Columbia, we're quite large, everyone has come to me and said, has said, you know, I have this really interesting data set. I need some data science expertise. We don't have the faculty, the students, or the staff who know how to work with data. Can you help me? And so this has been of course, very gratifying to know that there's such high demand for data science on campus. And the last part of my mission statement is indeed the title of my talk: ensure the responsible use of data to benefit society. I mean two things by this statement. First, to benefit society means really tackling those societal grand challenges like healthcare, social justice, climate, and so forth, that really challenge faculty and students in terms of their research agenda. The second part of this statement, to ensure the responsible use of data, it really harkens back to my emphasis on the privacy, ethical, and fairness concerns of collecting and using data. I summarized my long mission statement into 3 words. So this is all I want you to really have to remember from my talk, these 3 words and what they mean. Data for good, data to do good, data to do good for society and for humanity, and using data in a good manner, being responsible about how we collect and analyze, tell stories about data. Obviously, this is because I'm specifically thinking about data about people. So Columbia University's Data Science Institute collaborates with every other entity on campus of the 18 schools and colleges and institutes throughout the university. The medical campus itself has various schools, but of course, arts and sciences, engineering, the law school, the business school, the journalism school, the public policy school, even Barnard and Teachers College, we have collaborations with. We are loosely structured around these thematic centers. They should be familiar to you: financial analytics, health analytics, smart cities, sense, move, and collect, and so on. Of course, a foundation center. We have a center or a working group specifically interested in education and data science. And so these really just speak to some of the cross-cutting interests in data science as possibly applied to certain domains. We have a collaboration with the Columbia Entrepreneurship called Collaboratory, and it lights up courses, usually at the undergraduate or master's level, designed by 2 or more instructors from different disciplines. And my 2 favorite examples are a course that's designed by an applied math professor and a history professor called Data, Past, Present, and Future. And it is now, it's a very lightweight introduction to data science. And it is now accepted as a science, as satisfying the science requirement for the Columbia College students. Interestingly, for the engineering students, it satisfies a non-technical university requirement. Another example of a success of the Collaboratory is an 8-course curriculum that the current dean of the business school actually created, which really speaks from everything to the introduction to R and Python all the way to business analytics. And now over 50% of Columbia Business School graduates have some data science knowledge. The Data Science Institute has a robust industry affiliates program. At any point in time, we have collaborations with about 20 to 25 companies, and these companies come from all different sectors, whether it's IT or retail or finance or pharmaceutical, but also they're international. So we have Chinese companies, we have a Brazilian company, a Spanish company, so it's quite robust. And one of the advantages that an industry affiliate gets is to be able to work with our master students through a capstone course. We have a very special relationship with IBM, and right now its incarnation is in the Columbia IBM Center on Blockchain and Data Transparency, which itself has 3 tracks on education, research, and an innovation accelerator. So now what I wanted to do is just tell some stories about some of the research that is being done by faculty, postdocs, students at Columbia, either advancing the state of the art in data science or applying data science or using it in a way that tackles societal grand challenges or tackles issues of privacy, fairness, and so on. And this is going to be a bit of a whirlwind storytelling tour. So I wanted to start with a strength at Columbia on causality. And I want to just tell two short stories on causal inference. The first has to do with multiple causal inference. And the motivation is that classical causal inference considers univariate causes where, say, a subject receives a drug or a control. The problem that Yuxing Wang and David Bly address is different. It considers a situation where there are multiple causes for an effect. And it turns out that not only is this a common scenario, but it's an easier problem to solve with weaker assumptions than for classical causal inference. So let me just give you a particular example. Suppose you are a producer who wants to understand the causal effect of putting an actor into a movie. And you have to make casting decisions, and you want to predict the expected revenue. Should you put Sean Connery in a James Bond movie? And if you do, will you make more money than if you put Roger Moore in for James Bond? So your goal as a producer is to estimate the expected revenue given a particular cast A. That is, you want to estimate the population distribution Y of A, and thus for a particular cast A, estimate the expected outcome E of YA. Now, a naive approach, oh, by the way, for those of you who, that's the way the statisticians would phrase the question in this, what's called potential outcomes formulation. For those of you who are familiar with Udaya Pearl's do calculus, it would be expressed like this, as estimate Y given do A. So a naive approach to this is to fit a regression from actors to revenue. This estimates how much revenue changes when an actor is included. However, the problem with causality and in general is there might be unobserved confounders. These are variables that affect the causes, like the cast, and the effect, like the revenue. For example, the genre of a movie could be a confounder, as action movies make more money than artsy movies. Whether a movie is a sequel or not is a confounder. And then some actors, when appearing together, might generate more revenue than if only one appeared in the cast, so on and so forth. So these confounders bias the regression coefficients. Some actors will be overestimated, some actors will be underestimated. And so what do we do with this? I wanted to say before I tell you how Wang and Bly attempt to solve this problem is that there are many applications where there are multiple causes for an effect. How do genes affect a trait? The causes are the genes, the effect is the trait. How do prices of an item affect how much money is spent? The causes are the prices for each item for sale, and the effect is how much money is spent. So in classical causal inference, and I'm not going to belabor the details here, as I mentioned, confounders affect both the causes and the outcomes. And so what we particularly do in classical causal inference is the following three-step process. We, in our heads, think about all the confounders. We think about all the confounders that we can imagine, and then we measure the confounders in some way. Here, W sub I stands for the confounders, the variables that are dependent on both the assigned potential causes, the actors, and the potential outcomes, the revenue. Now, if we can measure all the confounders W sub I, then we can append W sub I to each data point in our movie data set and estimate an iterated expectation, which is the right-hand side of the equation on the right. And this step essentially corrects for all confounders. However, this three-step process starts with this assumption that we've identified all the confounders. And in practice, we assume it's true, But in reality, we're always on shaky territory because we may not actually have identified all the confounders. So that's the rub. This is what we do, and this is how we do classical causal inference. So this assumption I stated has a name. It's called strong ignorability, and it basically says this estimation that I write on the right-hand side works as long as there are no unobserved confounders. And we know, in fact, it's impossible to discharge that assumption. So the new idea is to take advantage of the fact that an effect might have multiple causes. And what we do here is we basically sidestep the search for confounders. And first what we do is we very operationally fit a local latent variable model of the assigned causes, infer the latent variable for each data point. This is the substitute confounder. And as before, estimate the causal effects. So this deconfounder replaces an uncheckable search for possible confounders with the checkable goal of building a good model of assigned potential causes. And let me just say that the high-level point to take away is there is an assumption, but it's weaker. The assumption is not that there are no unobserved confounders, but there's no unobserved single cause confounder. The other advantage of this approach is there's a checkable procedure. So before, remember I said there's no way that we can determine whether we have discovered all the confounders. So it was an impossible assumption to discharge. But here, we can check if the substitute confounder is good by some measure of goodness that we can actually define. And if we don't like the confounder, we can redefine it. And then finally, there's a proof in the original paper that shows that the inference is actually unbiased. So the punchline is, if we can find a factor model that captures a population distribution of assigned possible causes, then we have essentially discovered a variable that captures all multiple cause confounders. And that's kind of the insight. Now, going back to movies, what does this mean? With the deconfounder, given the data set of numbers I showed you earlier, Sean Connery's value goes up, and the actors who played the characters M and Q, their values go down. What this means is without the deconfounder, Sean Connery's value was underestimated, and Bernard Lee's and Desmond Llewellyn's were overestimated. And that intuitively makes sense because at least most of us would go see a James Bond movie because of Sean Connery was playing in there and not necessarily the actors who played M and Q. And the other beauty of this is once we have this model, then we can answer other kinds of what if questions, which is the point of building a causal model. Okay, so that's multiple causal inference. And what I really tried to argue is that there's a way to calculate a deconfounder which takes advantage of multiple causes for effects. And this has a weaker assumption than single causal inference. A completely different way of approaching causal reasoning is this technique that came out of actually the economics community called synthetic control. And this is doing causal inference without randomized control trials. The original paper had this really nice example from the California situation in California where they passed Proposition 99 to raise the taxes on cigarettes. And people wanted to know whether raising the taxes, whether Proposition 99 actually had a causal effect on the decrease of smoking in California. And so what the synthetic control idea is, you build a fake California out of bits and pieces of the other states that did not have such a Proposition 99. So for instance, the synthetic California is made up of a little bit of New York and a little bit of Massachusetts and a little bit of Texas. And then you can measure the synthetic control numbers versus reality, what happened actually in California after Prop 99 was passed. So the nice thing about this synthetic control idea is when COVID-19 hit, I asked my colleague Vishal Mishra to see what data he could collect so that we can do these what if analyses based on the myriad of policies that different states were putting out as the pandemic hit. Like, you should wear a mask, you shouldn't wear a mask, you shouldn't go to bars, you should da 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 da. And they did a COVID-19 counterfactual analysis for New York State. What if the lockdown had been put in place earlier? And what they show is, indeed, had the lockdown been put in place earlier, we would have had fewer infections and fewer deaths. And this was validated later on by some different colleagues of mine at Columbia in the School of Public Health that made an article in the New York Times that showed, in fact, that the delaying of the lockdown cost at least 36,000 lives in New York State alone. They showed also, my colleagues doing the counter COVID-19 analysis also wanted to know, well, there was a spike after Memorial Day in the number of infections. And so what was that due to? Was it due to the fact that temperatures are rising and people were turning on their air conditioning and the airflow, or what? And what they discovered that was the predominant cause for the increase in COVID-19 infections was due to indoor dining and indoor bars. Of course, these seem like old news to us now, but at the time it was, these are important policy decisions to think about. So that's all I want to say about causal inference. I'm very excited about causal inference and causal reasoning more generally, because as many of you know, in AI, machine learning, stop short of saying anything about causality. They talk about association and correlation and so on, but they rightly don't say anything about cause and effect. Now I want to turn to some stories where data science, machine learning, AI, data analysis, and so on are used in different fields. And I'm going to start with something pretty obvious, because this field has been using and generating big data for decades, and that is biology. Now, what is interesting in this particular work is that the biologists and the data scientists together were looking at the microbiome around pancreatic tumor cells, and they discovered that the microbiome was counteracting the effect of the chemotherapy that was meant to treat the cancer. So that's not good. But then they also discovered that if you inject the tumor cells with an antibiotic, then that antibiotic would counter the effect of the microbiome and thus make the chemotherapy effective. And so this was only tried out in mice. It's not yet in kind of the clinical stages. But it goes to show that, and this is just straight big data. There's not a lot of fancy data analysis here. My next example comes from my colleagues in the astrophysics department. I'm always admired the astronomers and the astrophysicists because I think they're very courageous and always wanting to try out new techniques, the latest and greatest coming from any different field. In this particular case, as many disciplines that deal with images, they looked at convolutional neural networks to see if they could better model, better model the images that they get from weak gravitational lensing. And basically what they did was they used the convolutional neural networks to predict the cosmological parameters of the lambda cold dark matter model from the images from weak gravitational lensing. And what they discovered was these fancy schmancy machine learning techniques outperformed the off-the-shelf statistical techniques that the astronomy community has been using, had been using so far. And so they got better, more precise coefficients or parameters for their models. My next example is in economics. I just wanted to say, when I was at Microsoft, I really saw the explosion of the combination of machine learning and big data and economics. This is something that I'm not sure all economics departments around the country are as forward thinking, but I definitely saw what can happen when you put economists together with machine learning experts. In this particular example, these researchers look at online labor markets like Amazon Mechanical Turk, and they look in lots and lots of data generated by these transactions that the Turkers do. And they were trying to come up with a model for how these labor markets behave. And what they discovered is that these labor markets behave more like monopsonies than, say, a fair labor market. A monopsony is where you have one buyer and multiple sellers, unlike a monopoly where you have one seller and multiple buyers. And this was counterintuitive. It was certainly not, it was a surprise when they came up with this discovery after looking at all the data. Another example in financial engineering is the use of reinforcement learning for robo-advising. This is an example where if you happen to be very wealthy and you have a personal advisor, financial advisor, all those personal and financial advisors could potentially be replaced by robots. And the robots can better learn your investor preferences in a shorter period of time, on the order of seconds, as opposed to on the order of months or years when you build up a trust relationship with your personal financial advisor. So there's a pretty standard reinforcement learning technique that one can just plug in the numbers, and after basically 8 or 9 iterations, this robot learns your preferences. The next example comes from a completely different part of the universe, which is humanities and social sciences. This is some work done by faculty in the history department in collaboration with people like David Bly. They looked at a very interesting data set. So Matthew Connolly runs something at Columbia called the History Lab, and they collect all the declassified documents from the US federal government every year. So it's the largest collection, he claims, that has ever been produced. And what they looked at in this particular project is to look at all the cablegrams that people, ambassadors and diplomats sent each other in the 1970s. They looked at the text, the subject field, and so on, and they just did basic topic modeling of the text to see if they could reverse engineering history. In other words, discover interesting events. And sure enough, they were able to distinguish between topics being discussed that were interesting events compared to business as usual. And every black dot here indicates some interesting event in that period of the 70s. So you'll recognize some, like the evacuation of Saigon or the death of Mao Zedong. Another example in the social sciences is the use of data very recently in the recent elections. And this is data science in political science. There is an app that you might have used, you might have known about, called Outvote, which was built by one of the Data Science Institute postdocs here at Columbia. And this app was then tailored by the Biden campaign. So it wasn't just get out the vote, but it was specifically trying to get out people who might have indicated a preference for the Democratic candidate. And the idea that the premise was, if we can we get more people to vote if we use the friend-to-friend connection through people nudging each other through text messages saying, hey, have you voted yet? Or go and vote. And they actually wanted to do a causal inference of this, and they had to very carefully make sure that they could set up the process such that they can compare it to the equivalent of a randomized control trial. And sure enough, what they discovered was this app was as effective as door-to-door canvassing when you have people knocking at your door and trying to get you to vote. So that was quite exciting, especially in the days of the pandemic when people were not going door-to-door to get people to vote. So what they found is this friend-to-friend nudging really helps. Okay, so now I want to turn to the responsible use of data, and then I'll stop with some societal grand challenges. So I have been arguing very recently about a new research area that I'm trying to promote, which I call Trustworthy AI. And it starts with the decades of research in trustworthy computing, which trustworthiness and trustworthy computing has come to be known to include properties like safety, security, privacy, reliability, availability, usability, and so on. AI systems force us to think about new properties of the computing systems we build. Accuracy, robustness, fairness, transparency, accountability, interpretability, and ethical concerns. These are properties that we never thought about the fairness of an operating system except in terms of process scheduling. But all of a sudden, we have to think about the fairness of an automated decision system that might determine who gets the milk money or who gets the low-income housing. So this is really new, and AI systems, of course, have their own challenges. Bring in new challenges in that they're probabilistic in nature. They're trained by data. Data comes from the environment. How to even model the data is always a challenge. That's the whole field of statistics addresses that challenge itself. So what I wanted to share with you are some couple of results, one dealing with robustness and one dealing with fairness. Maybe I may not try to cover everything. So with robustness and fairness, this is very recent work that we've been doing on looking at classifiers that purport to be fair, and we show that with very little perturbation to the input data, and that means they're not robust, we can make them unfair. So the canonical examples are risk recidivism used in criminal court cases. And what we show is that if you just reweight the data distributions that build a fair classifier, that's what's in blue, you reweight them very slightly, you can go from a fair classifier to an unfair classifier. And then of course, that's not good. So what we wanted to do is, how can you build a robust fair classifier? And much like a lot of the work done in this space for fairness and machine learning, we use an online algorithm, which is essentially a two-player game, to build a fair classifier that is also robust, and in fact, robust to a class of distributions. The other work I wanted to very briefly mention is safety, and this, again, going back to deep neural networks and the ease which one can change a classifier's decision to, in this case, from turning left to turning right, is dangerous if this classifier, for instance, is in your self-driving car's vision system. So what these people do is they show that with very natural perturbations to the input images, like darkening in the image, which is something natural that would happen in real life because you don't always drive in the daytime, a classifier can go wrong. And what they did was they showed that many state-of-the-art DNNs for ImageNet and used in self-driving cars and so on are quite vulnerable to this kind of attack. I think I'll skip this in the interest of time. And now let me turn to how data science is used for tackling societal grand challenges, used for good. Let me start with something quite obvious that, climate science has been working with big data, again, for many, many years in simulation and so on. This project is a huge open source project that's led by my colleagues at Columbia, but it involves many, many collaborators around the world. And it basically is building a huge open source stack. In fact, it's on the Google Cloud right now. And they're basically supporting ocean scientists, meteorologists, and other climate scientists to use this platform to do their science. So I'm just showing you a snippet of the kind of work that has been done. I wanted to share this story with you because this is also a postdoc in the Data Science Institute working with people in the Earth Institute and others at Columbia on looking at different grains grown in India to not just look at what the data is, but how looking at the data can possibly affect policy decisions for the government. And what they basically show is that, what they basically show is that in India right now, the primary crop that most of the country plants and is dependent on in terms of food is rice. And what they show is that the homogeneity of planting and eating rice is vulnerable to climate effects and weather effects coming down the pipe. And this means, for instance, monsoon seasons are changing in length and periodicity, and also volume of water, and similarly with droughts. And so if India doesn't change the diversity of the crops that they plant, and also where they plant them and when they plant them, then they're basically saying India is vulnerable to these climate effects if policy doesn't change. And that means incentivizing farmers to plant other crops at certain periods of time. And basically, they look at the data to justify those policy recommendations. My final story has to do with healthcare. This is an incredible federated data set that is being coordinated at Columbia University. It's called Odyssey. It stands for Observational Health Data Sciences and Informatics. Its goal is to get 1 billion patient records. Right now, they have 600 million patient records. So this is more than the population of the United States. These are 600 million unique patient records. And it's a data set that actually, as I mentioned, is federated. So it comes from 80 different databases from around the world. 25 countries are participating, hundreds of researchers. It's actually quite a large, complex, coordinated effort led by my colleague, George Ripsack at Columbia. And what I wanted to share with you are some interesting results that by looking at just observational data. So this is not clinical trials. This is not biological genomic data. This is just EHRs. By just looking at observational data, what one can learn. And so I'm going to tell just 2 short stories with this. First of all, they looked at 3 different diseases: diabetes, hypertension, and depression. By the way, I want to make an aside. In my opening remarks, I said that it's not enough to just visualize the data. You have to tell a story about it. Well, this kind of proves my point. I think these are beautiful pictures, but without my telling a story of how to even read these pictures, they just look like pretty pictures. So how to read these pictures, as each of these circle of circles represents one of those data sets. So for instance, this top one is the Columbia University Medical Center. So if you're a patient, in Columbia Doctors, you are a radius in the circle of circles. And the way to read the circle of circles is that the inner circle represents the first drug you get in a sequence of treatments to help you with, in this case, hypertension. So for the most part, the first line of treatment is this drug, hydrochlorothiazide. And if that doesn't work, then you're given a second drug, and that's shown by the second circle. And if that doesn't work, you're given a third drug, the fourth drug, and so on and so forth. All these circle of circles have been cut off after 4 drugs. Some of them go out way, beyond the page. So the two interesting observations that the researchers found by just looking at the data is, if I were to collapse all the circle of circles for all the data clinics that participated that had patients with hypertension, you would see that 1/4 of the population of people in this data set treated for hypertension are treated uniquely. So if you have hypertension and you're in that 1/4, and I'm your doctor, and you say to me, Jeannette, who else in the world in this data set is being treated like me? I would answer no one. So that's pretty amazing that 1/4 of the people in this data set being treated for hypertension are treated differently, are treated uniquely. The second interesting observation that came out from looking at all the data was in diabetes. Again, if I looked at all the 80 different circle of circles, they all look like the top 2 here. The one on the bottom, the top 2 here. So there's this chartreuse color first line of treatment that kind of works for the most part. But the outlier was JMDC. This was a clinic in Japan. And what they found is that the Japanese are somehow genetically disposed towards this particular metformin drug, which is typically used as a first line of treatment for diabetes. And so either you're given this drug and it doesn't work, and so you're given some other drugs, or the Japanese doctors know not even to prescribe that as a first line of treatment. And the visualization of the data bears that out. It also does raise a science question, which is why should this even be? So I'm going to very, 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 very quickly try to close my parentheses by talking about deconfounders again, saying when you have a data set like Odyssey and you have a causal inference new idea like deconfounders, why not put them together? And so that's in fact what the group of researchers did. They built what they call a medical deconfounder, looking at different kinds of causal effects of medications for certain kinds of diseases on the Odyssey database. And what they discovered was, in fact, the deconfound, and I put the equations here, the expressions here. The deconfounder, in fact, reduces both false positive and false negative rates. So some drugs went from being causal to non-causal, and some drugs went from being non-causal to causal. And it was hard. It's not easy to validate these kinds of results. So the best they could do was to look at the medical literature, and the effects that they found were consistent with what is written in the medical literature. So that is the end of my talk. Data for good. Please just remember that. That's what the Data Science Institute at Columbia University stands for. And I'm happy now to take questions.
Thank you so much, Jeannette, for a great talk. If people have questions, they can ask them in the chat. And I see that Martian Papczycki from Warsaw, Poland asked the first question, is the data set, the medical one that you just talked about, open to use by researchers from around the world?
Yes, if you go to the Odyssey website, you can see how you can sign up to be a participant. I want to say two things about that. First of all, what's so phenomenal about this Odyssey data set, if you're a computer scientist or information scientist or an IT person, you will really appreciate my next statement. These 600 million patient records are all in the same format.
Wow.
Yeah, so that is why you can do a single query over 600 million records and get this kind of these results. Now let me go to your question, and that is, first of all, it's still, and I'm just being very honest here. Anyone who wants to participate, it needs to go and sign up. But to sign up, you have to show proficiency in certain skills, and then to actually use the data. To be honest, and this is what George tells me and others, you probably still need a PhD level student or a trainee level student to help you actually work with the data. And now the other question that is often asked is, suppose I want to, participate add my data set or something. Then you are required to convert your data, and it could be through a transformation into this standard format. But for those of us who realize how difficult it is for things to be in the same format, this is quite a feat. Quite an engineering feat.
So
okay,
I see
more questions.
There are a lot of wows and amazing to the data all being in the same format. Sahi Burke from Technion asked the question, in the circle of circles, the observation regarding unique treatment of a quarter of the people is a bit odd because the number of drugs raised to the fourth power, the number of circles, seems smaller than the number of unique patients. Pigeonhole principle.
And then he canceled the question.
Okay.
So, I'm hoping, I'm good because I am just reporting results from the paper and from what George tells me. So it's just counting. It's nothing more than that.
So maybe I'll ask you a question, and if
Sure.
others have questions, to please put them in the chat. Do you have thoughts on how data science will permeate citizen scientists who want to do data for good?
Well, it's a good question, David. I think, as you know, and I don't know if Florence is still on the line, one of the goals of the Northeast Hub, along with our other three hub partners, is to spread data literacy throughout all levels of education, all kinds of institutions, from community colleges to libraries throughout the country. And so, that's part of the mission of all the hubs, especially now that the Northeast Hub started the Northeast Student Data Corps. That's one where we can help. Now, it will take time because there is so much demand for data science expertise, much more than there is supply. And this is how institutes like yours at NJIT and mine at Columbia and everywhere else throughout the world can help, right? By just producing talent at all levels, and talent with multiple skill sets. Some people are going to be really into visualization. Some people will be really into statistical machine learning, and these different levels of expertise are going to be needed for different tasks at hand. What I'm also seeing is that there's a huge demand by government agencies, by industry in all sectors. All companies in all sectors have an appetite for data science expertise. So all we can do in our in our small way in academia is to train the next generation and train as many as we can, and make sure that when we train them, they're really armed with the technical skills that are needed, but also they're armed with the ethical framework and thinking about, should I even be collecting this data, and do we need to secure this data so that no one else sees it, and so on and so forth.
That's great advice. NJIT is launching a bachelor's degree in data science. We hope to launch in fall. And those were certainly some good recommendations you've had that we've tried to incorporate into the program. Maybe one last question we have on the chat, and it comes from Neil Petrov. The Deconfounder sounds a bit like PCA, principal component analysis. Could you comment on the similarity or difference?
Neil, I really like your picture. It struck me. I am not an expert in the Deconfounder enough to be able to answer that. And so what I can do is I can ask David Bly to answer your question, but I think it is different. So that's the most I will say, stick my neck out and say about that.
Maybe there's just a couple more questions that came in, and this one is from Audrey M. Selim. Thank you for a great talk. You mentioned earlier in the talk the importance of interdisciplinary collaboration. Could you speak more on the ways DSI collaborates with the humanities?
Well, first I want to say that I mentioned a couple ways already. One is through the educational program with the collaboratory, where a history professor co-teaches with the applied math professor, and they co-teach this course, Data Past, Present, and Future. Another is actually through some research where history professor Matt Connolly and got together with people like David Bly and used topic analysis and so on to light up the data that the history professor collects. I actually think this is just scratching the surface of what could be done. If you think about the humanities, so much of what they have in terms of data now is the digitization of the text. Naveen, you need to mute yourself. And so digital humanities is the first step towards data science for the humanities, and digital humanities itself is still new to many campuses. And I think once the humanities disciplines are comfortable with working with digital data, then they're going to want the data science analyses as well. I did want to say in the social sciences like sociology, political science, and economics, they are already quite aware and moving forward with using data science techniques. I mentioned a few in political science, in economics, and so on. And I mentioned my time at Microsoft, where I just saw this explosion of interest between machine learning and economists people. Machine learning people and economists. So I think in the humanities, there's still a way to go, but because they work with text and actually multiple forms of speech and language, I think there's a lot of potential.
Jeannette, I want to thank you for an excellent talk on data for good.
You're welcome.
Really enjoyed it. Good to see you, and thank you again.
Thank you, everyone.